Landing on the moon is not easy. Just this year, the first 2 American lunar landing attempts since Apollo 17 in 1952 failed. First, Astra Robotics' Peregrine lander failed to reach the moon due to a propellant leak. And just a month later, Intuitive Machines' lunar lander took a tumble as it was making its final descent onto the lunar surface. It was navigating primarily with an autonomous visual guidance system when its landing leg struck a rock that this visual guidance system failed to navigate around, which broke the leg and caused the lander to tip over on its side. Despite this unfortunate collision, IM-2 still managed to return valuable data back to Earth. But undoubtedly, losing a $120 million lunar lander was devastating. NASA needs to relearn how to land on the moon, and more importantly, develop technologies needed to do it reliably. So, why is landing on the moon so difficult, even with decades of modern technological development? Firefly's Blue Ghost mission is the next lunar landing attempt, scheduled to launch this January, and I visited their Austin, Texas headquarters to get a closer look at Blue Ghost and learn how they are giving themselves the best chance at success while making landing on the surface of the moon easier for all that follow.
Mike.
Thank you, Neil.
I'll leave it in Flu. Relay to us. See if they got me now. I got good signal strength in Flu.
Yeah, you should have me now, Houston.
Eagle, we got you now. It's looking good, over.
What you just heard was Houston communicating with Michael Collins in orbit around the moon, asking him to relay messages to Buzz Aldrin inside the Apollo lunar lander. That static was the result of a poor connection with the command module. Aldrin began manually pointing the lander's S-band antenna towards the command module to gain a better connection. If this connection hadn't improved, the landing attempt likely would have been called off. Risking losing connection with the astronauts on the surface was not an option. In the latest US landing attempts, there is no command module to relay messages to Earth, and there is certainly no skilled human pilot inside problem solving. It simply doesn't make financial sense to send humans to the moon on these early exploratory missions. These lunar landings are part of NASA's Commercial Lunar Payload Services Initiative, a $2.6 billion fund set out specifically to fund private companies like Intuitive Machines, Astra Robotic, and Firefly, each mission receiving around $100 million in funding. Now consider that it cost around $1 million per kilogram of payload to reach the moon today. The 2 spacesuits worn by the astronauts on the moon for Apollo 11 alone weighed 160 kilograms. Launching humans, the life support needed to keep them alive, and the requirement of bringing them back safely simply does not fit into NASA's current budget for these missions. About 50% of all moon landings across all spacefaring nations fail. Around 55% of Mars landing attempts fail. These are unacceptable safety margins for humans. These missions serve an incredibly important purpose: to develop the expertise needed to learn how to land on the moon reliably, even without skilled human pilots, to test and develop the technologies needed to autonomously land on the moon and make it easier and safer for the crewed missions of the Artemis program. Technology has improved some things. It was unimaginable to send a lunar lander to the moon for just $120 million in 1972. While Armstrong was descending onto the lunar surface, he had to make multiple course corrections as unexpected boulders and craters appeared in the landing zone, something we can largely avoid today thanks to the Lunar Reconnaissance Orbiter, which began creating a massive 3D map of the entire moon with a 100-meter resolution, with areas of interest getting even higher resolution mapping, the same map that we can use to create these animations. We know where every crater and large boulder exists on the moon. It's this map that makes autonomous lunar navigation possible. Will Coogan, Firefly's chief engineer for their lunar lander, Blue Ghost, showed us these cameras right in the clean room where Blue Ghost is being built.
We have 2 different cameras on our vision navigation system. One is pointed straight at you, right there. You can see there's a lens cap on it. Yeah. And one is pointed straight down just behind it on a bracket. The reason it's on a bracket is you don't want anything except the moon in the field of view of the vision navigation camera. If you get glints coming off of MLIs around the legs, that can interfere with the vision navigation solution. It's not known for sure that it would, but it's a risk that's not worth finding out about. So we put on a bracket so that the feet are not within the field of view of the camera. The reason we have two is because when you're first coming down, you're braking, you're firing tangential to the lunar surface to arrest all of your horizontal velocity. So you need this camera to look at the lunar surface. When you slow down enough, you have to land on your feet, and you're just fighting gravity at that point. So then we switch to the other camera.
Do you have any redundancy for the cameras if something goes wrong with, like, other than, like, obviously they're pointing in different directions?
So they feed into the extended Kalman filter, as is everything else. So there's a certain altitude below which we're fine. But for navigation relative to the surface, no, there isn't a one-for-one swap for those.
So, Blue Ghost, similarly to IM-2, is heavily reliant on navigating with these cameras. They use the known detailed map of the moon created by the Lunar Reconnaissance Orbiter to figure out exactly where they are. It does this by taking the known positions of surface features, like the craters that pockmark the surface of the moon. The lander's computer then uses these images from its cameras to compare what it sees to the known map of the moon. There's no weather on the moon to occlude these features, but the software does need to account for changing shadows. Thankfully, it's easy to predict where the sun will be. Blue Ghost will be tracking along the Terminator line, the line that separates the illuminated day side and the dark night side of the moon, landing on what is essentially the moon's sunrise to give itself a full lunar day, which is equivalent to 14 Earth days, before its mission ends in a spectacular lunar sunset. With temperatures dipping as low as -130 degrees Celsius, the lander's batteries and electronics cannot survive the lunar night. The Visual Navigation System's algorithms work in a very similar way to star trackers, which spacecraft use to establish their orientation, but they can't provide position data. The star field looks almost identical from anywhere in our solar system. With the exact size and shape of every crater on the moon known, it's relatively trivial math to estimate altitude. The algorithms can estimate orientation, position, and velocity with a high degree of accuracy. The issues come when the cameras can't see these features. This happens at lower altitudes. This exact issue impaired Neil Armstrong's landing with Apollo 11, when dust kicked up from the thrusters occluded the surface of the moon. This is something that can impair these autonomous visual navigation systems too, and below a certain altitude, our digital map of the moon is no longer high resolution enough for the visual navigation system to work, as Will Coogan explained.
I should say that for all the excellent imagery we have, below a certain altitude, you do start to see things that even LRO can't see. And at that point, you have to rely on a different system because you're navigating relative to things that have never been seen before. So you start by looking at the things you do know. They might be over on the horizon by now, and they're getting pretty far apart. You identify something new, and now you know where that new thing is relative to something you already knew. And so now you start navigating relative to that. That's actually called a SLAM algorithm. Don't remember what the algorithm stands for. It was not named through lander missions. It was named through robotics programs. So it's maybe a little unfortunate for us that it has that acronym, but that's a commonly used algorithm.
SLAM stands for Simultaneous Localization and Mapping, and it's the same algorithm autonomous cars use to navigate busy streets. Then, around 10 meters above the surface, visuals are no longer viable because plumes of dust are expected to occlude the view. At this point, the lander is essentially flying blind, relying only on its inertial measurement unit to land softly. Even with perfect guidance, this is no easy feat. Precision thrust control comes from the Spectre Reaction Control System, a total of 8 hypergolic rocket motors that can be precisely controlled. One of the difficulties of lunar landers is just how light they are. With so much of their weight dedicated to propellant, they become significantly lighter as propellant is consumed, altering the thrust-to-weight ratio continuously, and continually changing the center of gravity of the lander. Intuitive Machines' lander was quite tall for this reason. They stacked their propellant tanks on top of each other to avoid lateral center of gravity shifts that could cause the lander to roll. However, this taller configuration raises the lander's center of gravity higher and makes it easier for it to tip over. Blue Ghost opted to have 4 propellant tanks sitting next to each other on a single level to lower the center of gravity. Because the 2 propellants are different densities, 4 tanks are needed to maintain the lateral center of gravity. This continuous weight change is something that has to be monitored and adjusted for by changing the thrust from the reaction control system. One way this can be done is through duty cycling of the engines on and off. With shorter or longer cycles, the thrust can be precisely controlled. At this point, you are probably getting a picture of why landing on the moon is so difficult. Even the legs of these lunar landers need to be carefully engineered. Will showed us some of the design considerations for this seemingly simple part of the lander.
You also see that there's no foot on that leg. There's actually a hollow cylinder. This is a 3D printed titanium piece. The reason we 3D print, not just because it's easier to manufacture, in fact, it's arguably not, but because we're able to vary the infill. So it doesn't have to be solid titanium. We can have cavities on the inside. Inside of that goes what we call a shock shuttle. It's a crushable aluminum honeycomb piece, and that absorbs the impact of landing and actually compresses when we land. So that not only absorbs the shock for the payloads, keeping them within the launch environment, but it also makes sure that all 4 feet are more likely to be in contact with the ground. If you have no compliance, right, you can have a foot floating, now you have an unstable platform. We deploy the vacuum that could push us over. So we want compliant feet. We will probably be able to show you a foot outside of the clean room when we leave here, but that also has a swivelable ankle. It's got a nice bowl shape, so it doesn't catch on the lunar surface if we came in at a slight angle.
Where does the sensor go for the foot? Like you were saying that one of the ways you land is through a foot sensor.
Yeah, so we actually start with the foot at an angle, and then when we land, it presumably goes flat, it goes to some other direction, and it unplugs something, and that's all the sensor is. So it's not complicated. There is a possibility that we land and that foot stays at the exact same angle, but we have 4 feet, so it's unlikely to happen on every single foot, and only one of them needs to trip to confirm landing. We do checks on those, right? Because there is a risk that during launch one comes out, during transit we have an intermittent connection, and we never have them power off the engine until we're below a certain threshold, and we're doing checks on them throughout flight to make sure we don't have any transient signals coming from that. And if we do, we say ignore that sensor during landing, just so we don't get a false contact.
So that foot sensor is one of the ways the ground crew can figure out if they've landed, but you may remember with Intuitive Machines, they weren't entirely sure of the status of the lander after it had toppled over. There are a number of checks to figure out if the lander has successfully landed. Sensors in the landing legs triggering is the first sign. They check for signals from the lander's data links if the engines have shut off, and they can check its orientation with the inertial measurement unit. However, there is a scenario where all of these checks could indicate a successful landing, but in reality, the lander bounced off the ground and is actually currently in free fall back to the moon. The moon is just really far away, and we don't have that much real-time data on what's happening up there. One of the missions of Blue Ghost and the overall CLPS initiative is to improve the situation, to provide more tools to future lunar missions. One of the major improvements that needs to be made is to communication and navigation systems. The US and Europe have a blind spot in their communication and navigation systems, something China has a leg up on. In 2018, China launched its first lunar relay satellite. China launched this satellite into Lagrange Point 2, a parking orbit beyond the moon, where it will have a consistent view of the far side of the moon and a direct line of sight with Earth, preventing extended blackout periods that a single satellite orbiting the moon would experience. With this relay satellite, China landed humanity's first lunar lander on the far side of the moon in 2019, and in 2024, they launched another relay satellite. Its huge parabolic antenna offers 10 X-band channels, allowing it to talk to up to 10 different lunar probes at the same time. Neither the US or Europe have anything close to this capability right now. But Blue Ghost is carrying a payload to evaluate using global navigation system signals emitted from American and European satellites for navigation, which could provide future lunar spacecraft accurate position, velocity, and time estimations. Currently, navigation beyond Earth is heavily reliant on NASA's Deep Space Network, an array of giant radio antennas which transmit positioning data to interplanetary spacecraft to keep them on course. Blue Ghost will be receiving positioning data from the Swedish Space Corporation until the visual navigation system takes over. However, NASA is already using GPS signals to provide position data to 4 spacecraft studying the Earth's magnetic field, which are in orbit around half the distance to the moon. But ultimately, NASA's goals are much higher than repurposing global position signals for navigation on the moon, and they plan to build out an entire network of nodes and satellites for future moon missions called LunaNet. LunaNet is the next phase that actually began with Intuitive Machines' first landing, which carried the Lunar Node 1 beacon, which was a test node for this future LunaNet system. It is a small CubeSat-sized S-band navigation beacon, something its principal engineer compared to a lighthouse, providing critical navigation information from the shore. A beacon he envisions flying on every subsequent lunar mission, gradually building up a network of lunar nodes. The original plan for this payload was to transmit signal around the clock, but with the lander's botched landing, it could only conduct just 2 15-minute transmissions, which the Deep Space Network successfully locked onto, providing brief but critical data on the new system. Blue Ghost's second mission, which is targeting a launch in 2026, will include a new communication satellite that will orbit the moon. Built by the British satellite manufacturer Surrey, this is a European Space Agency payload, which will provide communication for future polar and farside moon missions, a critical step for the European and American goals of future moon missions. These commercial lunar payload service missions will gradually build up moon technology and infrastructure critical for making moon landings safer and more reliable. And even with the hiccups, it's important to remember that Apollo hardware was thoroughly tested before Apollo 11's success, with their fair share of failures. We can and should be celebrating these missions like a modern reincarnation of the early Apollo program, but at a fraction of the cost.